So, what we are doing right now in module 3 of the chemical reactor theory course is to look at mechanisms and for pretty much non-elementary reactions and see how we can derive the overall complex rate expressions from those mechanisms. What we did in the previous lecture is we looked at a reaction A going to I going to P, okay, and then the derivation we had done earlier in the previous module, in the recap module. We took those derivations, put them in an Excel sheet and saw what happens when keeping K1 constant, we change the values of K2. Okay. So, when the value of K2 becomes much larger than value of K1, at that time I, the intermediate, comes under pseudo-steady state. Okay. So, lot of times in the past students have asked me that how do you know that a particular species is under pseudo-steady state, or how do you know that a particular reaction is under partial equilibrium. For the purpose of this course, we will give that to you. Okay. For when the question is a broader question, that is one of the challenges when it comes to larger reaction networks. We do not know how, we have various tools, we have multiple different tools, something called sensitivity analysis, reaction path analysis, network analysis and so on. We have various tools that allow us to explore exactly this question, but depending on the type of network, the type of reactions, and the overall kinetics and the mechanisms, so the answer might differ from situation to situation. It's a problem of ongoing research as well. Okay, so it's not a done deal with respect to simpler reactions. Yes, we know how to do, but if it is a network of reaction where multiple different reactants react to give multiple different products and so on and so forth, it becomes a bit complex. But let us get back to the situation we had. Okay. In this particular case, we saw that when K1 was much less than K2, under those conditions I was under PSS. Okay. What we mean by I was under PSS, that means rate of formation of I equal to 0. Okay. Rate of formation of I is K1 Ca minus K2 Ci is equal to 0, which yields us Ci, or I can say that is approximately equal to 0, K1 by K2 Ca. Okay. This is what we got. What we then did in the previous lecture is we computed the value of Ca, we computed the value of Ci, we computed the value of Cp. We also computed the value of Ca assuming pseudo steady state. The value of Ca does not change, right? Ca still follows dCa by dt equal to minus K1 Ca. So, the value of Ca did not change. Value of Ci changed, but changed only slightly. Value of Cp also therefore will change, but will change only slightly. Okay. So, when you used pseudo steady state as approximation versus when you did not use pseudo steady state approximation, but solved the entire problem, the results were very close to each other. Okay. But with pseudo steady state assumption, the solution was much simpler. That is what we saw in the previous lecture. Let us go back to the expression for Ci that we had obtained earlier. The expression for Ci, I think was, yeah, K1 Ca naught divided by K2 minus K1 . Okay. If K2 is much greater than K1, that implies 1 is K2 minus K1 can be replaced by K2. Second, e to the power minus K1t is going to be much greater than e to the power minus K2t, which therefore implies this particular guy is going to be approximately equal to e to the power minus K1t. Okay. So, Ci with an approximation of K2 much greater than K1 is going to be approximately equal to okay, which is exactly what we had got when we started off with pseudo steady state assumption. So, let us look at it two ways. We have derived the expression of Ci doing an a priori assumption of pseudo steady state. This we assumed that it is pseudo steady state. Why? Because we saw that after a particular time Ri was approximately equal to 0. Okay. So, therefore, I was under pseudo steady state. We did that in the previous lecture using Excel. Okay. So, when it was given that I is under pseudo steady state, Ri is equal to 0. Okay. And from there we were able to derive this. Okay. What I have shown now is also to show that if K2 is much greater than K1, okay, then the Ci expression that we had obtained 5 lectures earlier, that same Ci expression you will obtain by making that assumption K2 approximately equal to K1. Okay. So, these are two different ways, two alternative ways in which we are validating our idea of pseudo steady state. Okay. In the previous lecture in Excel you also saw that Ci that is obtained from this expression and Ci that is obtained from this expression are approximately the same. Okay. It was the third significant digit or the fourth significant digit where they started differing with each other, which means the error is less than 1%. Okay. 1% error is already less than the experimental errors. So, as engineers we are happy with that error. It is much more easier to deal with simplified systems like this than it is with the entire complexity. Okay. So, this is about pseudo steady state assumption. The second assumption that we are going to use is partial equilibrium. Okay. Let us take the other reaction. Let us do K1B. Okay. Maybe last year I had used K1 and K minus 1, I do not know. Okay. So, write down what is going to be Ri. What is Ri for this? Of course, when you are working this out, please feel free to talk to each other. If there is anyone who did not get this, okay, what I would suggest you to do is you think about this in this way. Okay. Okay. What is capital R is summation of mu R, right. So, this is just plus K1F, okay. What will happen if we take a pseudo steady state assumption? What will you get? What does pseudo steady state mean? What is 0? Ri is 0, capital Ri is 0. Okay, you will now see why, unlike textbooks, I have chosen to use capital R for species rate of formation and small r for reaction rates, okay, just so that it is easier for us. If we use small r for both the things, pseudo steady state and partial equilibrium will get confusing, okay, that is the only reason. Okay, so don't come and tell me that, oh, the textbook has a different notation. I mean, yeah, we are using different notation so that it becomes a little bit easier for us. So, if we have pseudo steady state, our Ci is going to become K1F Ca plus K2B Cp divided by K1B plus K2F. Okay. What do you think would be partial equilibrium based on what I had mentioned in the previous lecture? What would be under partial equilibrium? Okay, forget the word partial. Let us say we were talking about equilibrium. What can possibly be under in equilibrium? Intermediate and the reactant can be in equilibrium. What else? Can intermediate and product be under equilibrium? Yes. What else? Reactant and product be under equilibrium? Can reactant and intermediate as well as product and intermediate be under equilibrium? Yes. Why are we not committing? I should either see vigorous this or vigorous this, no? Yeah, they can. In fact, you give sufficient time, they would, right. So, A and I can be under equilibrium, that means the first reaction as written over here can be under equilibrium, okay. I and P can be under equilibrium, or AI as well as IP can be under equilibrium. If AI and IP are under equilibrium, then A and P also by definition are under equilibrium, right. Right. Okay. So, let us say if the first reaction, the first reversible reaction A going to I was under equilibrium, okay. Just do not think that this guy, I can't put it, I was closing the, so just ignore the second reaction, right. Just put your hand over the second reaction. I do not know if I can do that, okay. Yeah. So, just think that, oh, okay. Just think this does not exist, okay, only this. If this is under equilibrium, what does that mean to you? It can mean R net equal to 0, or it can mean R forward equal to R backward, okay. This is equilibrium. partial equilibrium means approximately equal to 0. Okay. The only difference happens in the first step, rest of the derivation will be exactly the same, right. So, what does this mean? If the first reaction is under partial equilibrium, then that would mean K1 Ca is approximately equal to okay. This will imply Ci is equal to Ca. Okay. That is what partial equilibrium means. Are we calling it partial equilibrium because next step is not in equilibrium? What do you guys think? Okay. So, let us assume that the answer to this question is yes. What happens if A and I are in equilibrium, but the next step is not under equilibrium? What would happen to I? Okay, right now, and again, if you are a computer scientist or a computer engineer, there is a term called sandboxing. Okay, that means you put a box around I to P, okay, and just only look at I to P, do not look at anything else. So, just as we had done earlier, we will do this. Oops. Okay. Let us assume this does not exist, we are only looking at this. Okay. I to P is not under equilibrium. What is going to happen to I with time? I will change in what direction? Decrease most likely, right, as written most likely I is going to decrease because it is not under equilibrium. Okay. Now, just we will put one more scratch over here. Okay. So, now let us only focus on I. For whatever reason I is decreasing with time. Why? Because it is being taken away by the second reaction. Okay. Let us think now I is decreasing with time. Let us now remove this. Okay. Think about what is happening. I is decreasing with time. So, what will happen to this reaction? There will be a tendency for A to convert to I. Okay. So, now did you get the idea of partial equilibrium? If it was equilibrium, A would convert to I in the same way I would convert back to A. Okay. But some of I is being taken away in forming of P. So, A will convert to I will convert back to A, but not exactly, just a little bit lesser. By how much lesser? If I is also under pseudo steady state, by exact same amount as I to P is happening. Okay. So, to answer his question, yes, we are saying this is in partial equilibrium because rest of the system is not under equilibrium. Okay. So, it is not exactly under equilibrium in the sense that A is getting depleted, I is getting depleted. If it was under full equilibrium, A and I will remain the same. They are not remaining the same, A and I are both getting depleted. Okay. So, think of it like I is playing tug of war from both sides. Okay. This tug of war is exactly matched. Okay. So, I am not able to move like this, but this tug of war I am losing. So, I start moving over here. What is happening to A? A is also moving with me, right. That is the difference between partial equilibrium and equilibrium. In equilibrium, I am winning both, not winning, but you know, I am over here. Why? Because we are both under equilibrium. Partial equilibrium means A and I, both of us are moving together, okay, and this person B or P is winning. Okay. So, how do you use, this will remain with me forever. Okay. So, let us take this particular case. You have already looked at the case where I was under pseudo steady state. What did you do with I is in pseudo steady state? Recall? Ri equal to 0. Okay. Where does the term pseudo steady state come from? Okay, because all of these analysis are usually done assuming batch system. Why it is done, these analysis are done with batch system? Simply because if it is a flow system, okay, addition and removal of species in your control volume can affect your analysis. Okay. Mechanism, starting from mechanism and going on to rate expression, you only want to focus on reaction rates. You do not want it to be obfuscated by flow conditions. Okay, you do not want it to be confused by flow conditions. So, that is the reason why historically, traditionally, we have been doing this in batch reactors. Today, we do not even care whether it is batch or not a batch reactor. Why? Because what we are doing is Ri equal to 0 is pseudo steady state assumption. Partial equilibrium assumption is R1 net equal to 0, or okay, by the way, again it is also possible that the second reaction is under partial equilibrium and not the first one, very much so. Okay. So, now let us say that R1 is under partial equilibrium. If R1 is under partial equilibrium, what will be the value of Ci? Okay. Yes, what do you get if reaction 1 is in partial equilibrium? What does this imply? If you compare the left hand side and the right hand side, what does it imply? Can you see something else? What would be the relationship between K1B and K2F for the left hand side expression to reduce to the right hand side expression? What is much greater? K1B is much greater than K2F, right? Okay. So, that is what mathematically happens. If the rate constant is much greater, okay, then what happens is that tug of war is much more well balanced. Okay. Both K1F and K1B are very large. Okay. Note that R net is non-zero. Okay. So, R1F minus R1B is not 0. So, they are not exactly equal. Okay. The test for partial equilibrium is if the reaction is exactly under equilibrium, what should this value be? You can't see that clearly? At partial equilibrium or at equilibrium, what will this value be? 0.5. Okay. This is called partial equilibrium ratio. Okay. If this value lies between, let us say, 0.45 to 0.55 plus or minus 10% of 0.5, okay, then we will consider that that particular reaction is under partial equilibrium. Okay, this is what we do in our research. Okay, what you will do for this particular course is we will be telling you that, let us say that this reaction is under partial equilibrium, please derive so and so. Okay, so that is what this says. If steady state, then this is the value of Ci, this is something that you yourself derived. Okay, and if we are to plug this in, this is what we will get. Okay. Option number 2 is partial equilibrium. Okay. If it is under partial equilibrium, okay, then what it means is that the first reaction is under partial equilibrium and then you get overall the second reaction, and this is something that you will need to solve. So, if you look at the right hand side, this is the net rate of formation of P, right. This is what you get as the net rate of formation of P under pseudo steady state assumption, and this guy, if you write it, or say K2F So, partial equilibrium, A to I reaction is in partial equilibrium, AI reaction is in partial equilibrium if that reaction is very fast. If that reaction is slow, then it will not be under partial equilibrium. Okay. These are same things that you yourself have done, you yourself have answered. I am not talking about anything different. Okay. When we were over here, when you did that comparison, that is exactly what you guys answered. Okay. The couple of examples that we are going to use is Michaelis-Menten, and we will do HBR. HBR is not as home assignment. We will do HBR as tutorial. Okay. So as I promised in the previous class, we will run this as a tutorial. So we will just, so let us look at the basic enzyme catalyzed reactions, the Michaelis-Menten reaction, and let us try to derive. Okay. The reaction is okay. Okay. If reaction 1 is in partial equilibrium, what do you get? Typically in mechanisms, the mechanisms are written such that each reaction is elementary reaction. Okay, that is what basically mechanism means. You are writing down your reactions as a sequence of elementary reactions. So, elementary reaction means the reaction is written as it happens at a molecular level, and that is why each reaction in a mechanism is an elementary reaction, because you are writing the mechanism, each reaction in a mechanism as you believe it happens at the molecular level. Yes, these parts, everyone? Okay. Just think simply. Step number 1, partial equilibrium. Let us say you have a complex 10 reaction mechanism and it is given to you, reaction number 3 is in partial equilibrium. Apply R3F equal to R3B. Reaction 7 is in partial equilibrium, R7F equal to R7B. Reaction 8 is in partial equilibrium, R8F equal to R8B. Okay. From these 3, you will eliminate 3 unknown intermediate concentrations. They will be represented in terms of other measurable quantities or other intermediates. Okay, that is exactly what we have done over here. Concentration of ES we have written in terms of a measurable quantity, concentration of S, and an unknown quantity, concentration of E. So, we need something else. What else? I think all chemists and chemical engineers would have done this in your undergraduate. What else is there? Sorry? Product? Yes. Have we done yet? We know we can measure or we can know the concentration of S. May not be easy to measure the concentration of E. You can do it, you can take an enzyme and tag it with a fluorescent green protein, okay, and when the enzyme is in free state it will be green in color, when the enzyme is in bound state it will change its color. So, based on the strength of the green color you can measure amount of E, but those are not necessarily straightforward measurements to be done. Usually they are not done. So, CE is usually not measured, it is only CS that is measured. So, what else do you have handle on? When it comes to gas phase species, you will have to find out one more step in order to find out what happens, okay, when it comes to gas or liquid phase reactions. When it comes to gas or liquid phase non-catalytic reactions. When it comes to catalytic reactions, you have one more idea under your arsenal, and that is the total of enzyme or the total of catalyst will not change. So, the enzyme that is free, enzyme that is bound to substrate, enzyme that is bound to inhibitor, enzyme that is bound to the product, sum of all of this will be equal to your initial enzyme concentration. Okay. So, if we were to take this item number 3, do not write it like this. Okay. Okay. So, CE, CES, CEP, CESP, CEI, CESI, blah blah blah, everything. Okay. What I am talking about over here, enzyme can be bound to substrate, enzyme can be bound to product, enzyme can be bound to an inhibitor, enzyme can be bound simultaneously to an inhibitor and a substrate, enzyme can be bound simultaneously to an inhibitor and a product. All of those possibilities are there, that results in different types of Michaelis-Menten kinetics, Michaelis-Menten reactions. Okay. All of these will follow the same concept, you add all of those concentrations up. For this particular example, what does this mean? CE plus CES. What is CES? This guy. Okay. So, CE this will basically give us okay. If we take this and substitute it over here, this we are going to get K2 K1F. Okay. This we can write this as this. Okay. And this has the standard Michaelis-Menten form. Okay, Ks is called saturation constant, Km is called the Michaelis-Menten constant. Now, the question is, what if Es is under pseudo-steady state? Instead of partial equilibrium, first reaction under partial equilibrium, instead of that you are given that Es is under pseudo-steady state. What will you do? Okay. What is the PSS assumption? Es under pseudo-steady state. What does that mean? I under pseudo steady state, what did that mean? I under pseudo steady state meant Ri equal to 0. Es under pseudo steady state therefore will mean what? Res equal to 0. Okay. Res is nothing but K1 CS CE right. So, step number 2, what do you get? Substituting or rearranging. This is the form that you will get. What that alpha is, what that Ks bar is, you can work it out. Okay. And finally, okay. So, for the simple Michaeli-Menten kinetics, okay, just looking at the rate expression, you will not be able to differentiate between whether the rate expression implies pseudo steady state or partial equilibrium. In your assignment for in the next module, we will take up an example where different mechanisms will lead to different rate expressions, and then you can use experiments to say that this mechanism is not valid, okay, but just from rate expressions you cannot guarantee that this other mechanism is valid. Rate expressions can be used to eliminate mechanisms, it cannot be used to confirm a mechanism. To confirm a mechanism, you will need things like running the reaction with the fluorescent protein. Okay. So, we are already running a bit late. To summarize, I will take maybe 2 more minutes to summarize. to summarize most of module 3. If a species X is in pseudo steady state, use R of X equal to capital R of X equal to 0. If reaction J is in partial equilibrium, use RJF equal to RJB. Okay. Use one of these or both of these in order to express concentration of an intermediate in terms of concentrations of the rest. Okay. Additional information is basically CE plus CES equal to E naught. Okay. Likewise, in heterogeneous solid catalyzed reactions, you will also see an equivalent expression. Okay. Once that is done, you plug it into your overall rate expression and solve. That is the overall process that you will use throughout for your module 3 and 4 and rest of your life in order to derive a rate expression from kinetics. We use this even in our research, even the example of 54 reactions that are talked about in the very second lecture, even there we are using these exact same concepts. It is just that you will have to use PSS for 3 different reactions and partial equilibrium for 7 different species. Okay. Math gets complicated, but essentially it is the same techniques that we have covered in this class so far. Okay. Alright, we end the class over here. The next class is going to be a tutorial, okay, where we will take certain examples. Rest of the slides exactly deal with what I have talked about over here. We are not doing anything else. Instead of taking what do you call free radical reaction and then showing you how to derive, in the next lecture you will derive it as a part of the tutorial. Okay, that is what we will do, so that reinforces the concept more strongly. Okay. We will take HBr reaction and one more enzymatic type of a reaction. Okay. Yeah, we can use both assumptions, not for the same species. So, very good question. In a derivation, can you use both assumptions? Yes. Okay. If for example, it was A going to I1, going to I2, going to P, you will need to use multiple assumptions. Okay. But in this particular case, in the case that we are showing over here, okay, you cannot use a partial equilibrium assumption and pseudo steady state assumption. Okay. Partial equilibrium assumption already tells you R1F minus R1B equal to 0. Pseudo steady state assumption will say R1F minus R1B plus R2 equal to 0. If you are using both those assumptions, which will give you R2 equal to 0. R2 equal to 0 is not possible. Okay. Why you are getting that? Because you are incorrectly applying the same assumption. Incorrectly applying 2 different assumptions to the same thing. In this case, the fate of ES. Okay. Hopefully that answers the question. Okay. In a larger mechanisms, yes, you will use multiple of this assumption but you cannot use these assumptions to calculate the same thing. Okay.